Hello, Brian Miller-Hicks, engineering geologist, and continuing with our narrated PowerPoint series, I'm going to talk about soils, soil behavior, the impact of soil conditions on structures, the impact of structures on soil conditions, the role of groundwater, the strength of materials, types of foundations, type of ground modifications, slopes and slope stability. So I'm going to cover a lot of stuff here. This is going to be content rich. It may be kind of long, so bear with me. So let's start with some basic stuff. Stresses, Earth stresses. What does that mean? That's the load imposed by gravity, by confining pressures, by the weight of buildings, by the weight of water, a lot of forces that come into play to impose stresses on soils and or bedrock. So here's some very basic graphic depiction of stresses. The graphic on the left indicates or shows Earth under stress by means of faulting. There's a three axes of stresses as shown. So let me get this laser pointer. So a normal stress acting vertically, component of gravity. There's two sideways stresses, if you will, maximum stress and minimum stress that act as confining stress on a block of soil under the Earth's surface. Okay, so know that forces are acting on subsurface materials all the time at different strengths, different amounts or magnitudes of stresses, transient stresses imposed by earthquakes, landslides, etc. So this is a depiction of Poisson's ratio. It shows that a vertical stress, when you're pressed down on this cylinder of soil, it will compress in height and expand in width if it's unconfined. So it's a ratio of change in the width per unit width, or to the change in its length per unit length as a result of strain imposed by stresses. Different ratios for sand as opposed to clay. Clay will perhaps, under saturated clay will perhaps deform more readily and at a higher magnitude than a dense sand, for example. So what are the stresses that are imposed on subsurface materials? There are, of course, natural stresses imposed by dry weight, the weight of pore water or the weight of water in the void spaces between and among pores, mineral grains, sand grains, layers of clay, etc. Effective stress, and this is a very important principle in soil and soil mechanics, it's the weight of the soil minus water pressure. Why minus water pressure? Well, the imposition or the presence of water in soil pores tends to give soil, earth materials, a buoyant force effect that tends to separate grains and reduces total stress. So effective stress is a lower number than the stress you would achieve under drier conditions. Buoyancy effects below water table. So when we're investigating a piece of property for construction, whatever it may be, a building, a bridge, a roadway, we have to assess tectonic and geologic history. That can be significant. Tectonic history, of course, has to do with the imposition of faults, tectonic stresses, whether they be compression or extension, tension. You have deep burial, you have uplift, you have erosion. If these soil materials have been under great amounts of loads from glaciers that have previously laid on top of these materials, if you unload the glaciers, unload the ice, the materials, subsurface materials, can actually rebound, start rising back up. Tectonic compressive history, you can have in very, very high, higher than expected stresses. Tectonic extension may lock in higher than expected tensile stresses. These can lead to dangerous deformations. Let's say you have an overstressed, over-consolidated material and you want to dig a tunnel through it. Well, and you're digging a hole through a very compacted, consolidated mass, and what you're doing is you're relieving ancient stresses. You're causing these stresses now to go to that region of low pressure that you've created by digging a tunnel, so you can have deformation of tunnel walls, compression into the tunnel space, which can lead to dangerous conditions like tunnel failure, rock burst, etc. So it's really important to be cognizant of the stress history of a material that you're trying to alter, change by construction, whether it be excavation or the imposition of additional loads. So let's talk a little bit more about effective stress. As I explained, effective stress is the stress reduction caused by the imposition of water, which gives us a buoyant effect. So here is a simple diagram. Total stress, meaning weight of soil, grain-to-grain contact within the soil mass or the rock mass. When you introduce water, this symbol here, you're tending to separate grains so that the grain on grain stress has been lessened, and now it becomes effective stress. So here's a practical effective stress design problem. I'm going to be talking about practical things in this presentation. So you have a simple layered subsurface scenario here. You have sand over clay, and you have here a culvert or tunnel within the clay. So this is dry sand for the first 4 meters. So you have 4 meters times the density of sand. 4 times 16 is 64 total vertical stress at this point. Now you have water table. So the sand underneath this water table, the density increases. So now you have 4 meters times 19 kilonewtons per cubic meter, which gives you a total vertical stress of 140 kilonewtons per cubic meter. So you add those two together, 64 plus 64 plus 64 plus 4 by 19 equals 140. So the total stress of this 10 meters of sand, including the saturated sand, equals 182 at this surface. Now you have clay. So you have 2 meters of clay, 8 to 10, under saturated conditions, which gives you a value of 2 meters times 21 kilonewtons per cubic meter. So add the 140 to that 42, you get 182 at this point. Excuse me, 10 meters. I might have misspoken previously. The 182 is at this point. The 140 is at this point, this level. Now what happens when you get effective stresses below the water table? Well, that takes away 40 kilonewtons at this point. So you have an effective stress of only 100. And at the crown of your culvert here, you now have an effective stress of 122. instead of 182. So during construction, when you're draining, let's say you want to drain this water down to below the elevation of the tunnel, instead of having 182 here, you now have 122. So you're going to have to deal with design and build this tunnel under dry conditions, but when the water comes back in, that raises the total effective stress to 182, as you see here. I'm sorry, 122, as you see here. So this is a practical problem that engineers deal with all the time in design and build circumstances under unsaturated and saturated conditions. So take your time and look at this diagram, look at my numbers. Hopefully I explained it clearly. If not, it's fairly simple to go through this figure and to go through these calculations and to read this down here. At the tunnel crown is 122 during construction. The water table is lowered, done deliberately. If the water pressure drops, so the effective stress would increase. If the water table is lowered, the water pressure would equal the total stress of 182. So if you drain all the water out, the total stress increases at this point. If you let the water come in, the total stress would decrease, taking into account the effective stress. Okay, just an example of some of the conditions and calculations and parameters that you have to figure in when you're designing, when you're building, and when you're maintaining a structure. Okay, effective stress is a critical factor in shear strength, bearing capacity, slope stability, soil settlement, and liquefaction during earthquakes. Let's get down to practical considerations for construction and foundations. So you have excavations. You may have deep excavations. If you have deep excavations, let's say 30, 40 feet, such as an underground garage below a skyscraper, you might have shoring walls. You might have soldier beams, which are tied together by shoring walls. You may have concrete piers. All these types of structures to hold back the walls of the excavation while you continue to excavate, especially in unstable rock and soil. When the excavation is proceeding, you have to be aware of drainage measures if you have shallow groundwater that wants to enter the excavation, so you have to provide drainage. You have to have safety and stability measures that are coordinated by everybody on the job. So building loads, keep in mind that the density of a building is typically less than the density of the soil on which it sits in terms of pounds per cubic foot. However, it can impose a load on the underlying soils. So you have the load of the building, you have what are called live loads that are imposed by weather conditions, rain, snow. You may have additional loads from wind, excuse me, and you have dynamic transitory loads imposed by earthquakes. So all these loads have to be taken into consideration, as well as the soil conditions down below, so that you can design an adequate foundation, whether it's a shallow foundation or a deep foundation. So you have factors that go into design of a shallow foundation, including bearing pressure, soil bearing capacity, the strength of the soil, the ability of the soil to withstand loads, maximum loading pressure. The design has to meet a factor of safety before, so it has to be designed so it doesn't fail under certain conditions. You may have presumed bearing pressure where you're familiar enough with the local soils, local rock, the building codes that you can design based on assumptions, although it's always recommended to investigate a property by drilling borings or excavating trenches and taking samples and testing those in the lab. This is a lot of information. It has to do with bearing pressures for rock and soils taken from Hencher, Practical Engineering Geology. A couple things to point out here. Governing factors for rocks. You have fractures, which are planes of potential weakness. You may have weathered, decomposed chunks or masses of rock, soft pockets. If they're unsuitable, they might have to be excavated and replaced. Governing factors for soil are shear strength, plasticity and density. Compressibility, settlement, and expansion are always issues. Blow counts derived from sampling during drilling are very important in assessing the strength and density of any soil. Okay. Now, when you're excavating for footings, you want to excavate before you pour concrete, place steel. You might see weak or soft weathered pockets, so you got to dig those out and replace with stronger material. You want to have uniform conditions throughout foundations. So you might have, for example, if you have a native soil, you might want to excavate 3 feet down and then replace all that soil with uniformly compacted fill to take away any variations in density from a natural deposit. So that gives you uniform strength. And down here, avoid transitions between weak and strong in formation and fill. In other words, let's say you are building on a hillside. So you have to cut the upper part and fill the lower part so that you get a flat pad. Now that may result in the back half of the lot or the pad being formational and the front half being compacted fill with somewhat different densities and properties. So you're going to have to excavate the back half of formation down a few feet so that you can replace the whole pad bearing surface with a uniform compacted fill. And it eliminates the cut, fill, transition, and change in material. So with deep footings, you have other conditions to consider. You have, with deep footings and a water table, you might have buoyant forces and uplift. As I mentioned before, when you're taking out soil to put in a structure, you're actually creating a space where, and replacing it with a structure that has lower density than the pre-existing soil. And if you're in a buoyant condition of groundwater, you may get uplift trying to push up on your structure because of the buoyant forces of water. So you want to drill down farther below the structure and sort of anchor everything into very firm material to counteract the buoyant forces. Different types of deep footings or foundations include, based on the material used, you might have steel pile, which is basically a beam made of steel. You may have the pile made of concrete. So what does this mean? You have an end-bearing pile where you design the pile based on the bearing capacity of the soil on the end only. Friction pile, you may design a pile based on the friction that's built up along the sides of the pile surrounded by the soil or rock. So that might be an addition to strength based on friction on the sides of the pile as well as the strength of the material at the bottom of the pile. You can install piles by driving them or drilling a hole and putting concrete into the hole. You might screw in a pile, or you might jack in a pile with a jacking mechanism. Different types of piles: low bearing, sheet piles, compaction piles. There's piles that you drive in and you base the design length and depth on the displacement of soil. Okay, so there's different considerations that go into the design of a pile foundation, deep foundation, and the type you might use at a particular site. So again, here's different types of pile foundation graphic. These are steel H-beams. I'm sorry, these are steel sheet steel or sheet piles. Piles that are driven into the ground. You have soft soil, you have hard soil. Here's the frictional force caused by skin friction, which gives you more strength around the pile itself. The deeper you sink a pile, the more skin friction you have, and the better that pile will be held in place. Here's a drill and cast in place pile. So you drill first, and this illustrates a steel jacket placed in the excavated boring. Then you place concrete in that void, and then you place steel in the concrete, and you have a completed pile here. So these are very, very strong structures, and typically a structure may have several or many concrete and steel piles built into the subsurface to give it foundation support. So there's other ways of improving, mitigating foundation conditions, deep ground improvement. So what does that mean? That means we can go in and improve the ground. This is one way to do it. You have a crane with a big weight, 15-ton weight, and you may drop it 20 meters, or 66 feet or so. Will compact the ground to a depth of 10 meters. So each one of these dark spots here is where this crane has been dropping the weight and compacting the soil below if you have a soft soil condition. Bam, 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 bam. That compacts the soil. You have better foundation conditions. You want to test or measure if your method has worked by using standard penetration tests to get the relative density of soil before this procedure, and you want to do the same thing after the procedure to see whether indeed the soil has densified to the desired depth. Here's another method. This is called stone columns, where you drill a boring and you fill this boring with stone, just chunks of probably cobbles, rounded cobbles. It gives you density, it gives you weight, it gives a support structure for whatever structure you're building. It may prevent liquefaction, because liquefaction from seismic shaking occurs in saturated, loose, fine sands, and here you're introducing a coarse material element to mitigate that. Okay? Soil mixing. You may have very deep clays with high expansion properties. In other words, these clays may swell when water is added. So they're weak clays which undergo volume change from wetting and drying. So you want to improve that condition. How do you do that? You go in with lime and cement and mix that lime and cement together after you've excavated through the clay. That gives you something that's sort of equivalent to a stone column that I told you about in the last slide. And you're improving the basically the strength and lowering the expansive capacities of the clay soils. Construction grouting. A grout is a type of cement that is often used to fill in voids in a natural soil or bedrock condition. For example, in Florida, there's sinkholes and other types of voids, caverns even, because of the limestone and the dissolution of the limestone by groundwater. So if you're building on top of this type of terrain, you might want to fill those cavities, and you do that by introducing grout, which is a cement mix to fill the voids and give stability to the foundation conditions. Let's talk about slopes. So slopes, of course, are important to any type of construction. You want to know that the slope you're building on or excavating into is stable and will remain stable. So we have certain types of construction practices for these situations. Here in California, we have a famous case that happened in 1995 and then 10 years later in 2005 at the coastal town of La Conchita. All this material is weakly cemented, faulted shale, siltstone, sandstone, just sheared up, just very weak. And there's an orchard on top, which of course didn't help because you introduce irrigation water from the orchard into the soil. So in 1995, this failure occurred, this landslide occurred and buried some homes. In 2005, the same thing happened. After the 1995 event, some walls were put up, hopefully would stop any further damage. Didn't work. In 2005, the walls were overtopped and overwhelmed, and some people died, and some homes were destroyed. So you have to know what you're dealing with. You have to investigate these types of situations. You have to look at maybe setting back homes away from the hillside, or putting up giant walls which won't be overtopped, or removing and rebuilding the slope itself. So when you're in engineering, typically in slope construction, a natural slope can stand at a 2-to-1 ratio, 2 horizontal to 1 vertical. Sometimes, if the material is strong enough, it can stand at a 1-to-1 ratio. Bedrock can stand at a 3/4 horizontal to 1 vertical. That's a very steep slope. So the stronger the material, the steeper you can leave the slope. Now, man-made slopes, whether they be cut slopes or fill slopes, we want to typically design them at 2-to-1. It's not a great idea to design and build an artificial fill slope at any steeper than 2-to-1. So that introduces a safety factor at a 2-to-1 ratio. Okay, what is slope failure? Basic slope failure, you have driving forces working against resisting forces. The driving forces include gravity, weak materials, wet materials that are conspiring to move the slope downwards, material and slope downwards. Resisting forces include friction and shear strength, and maybe some vegetation roots, tree roots, those will help in shallow failure situations. So up here you have the gravitational force, you have the shear force driving down, You have the shear strength resisting. Now, in steeper slope, the shear force is, and gravitational forces may overwhelm the shear strength. Very steep slopes, the shear strength is not enough to hold this block from sliding down, so something has to be done to change that situation. How do you analyze the stability of a slope? You use an analysis called method of slices. Slope factor of safety you want to get to should always be greater than 1. The ratio of shear resistance to shear driving force should always be greater than 1. You can graphically analyze a slope by dividing a slope into a series of vertical slices. So this is what it could look like. So here is a slope. Here is your presumed failure surface, this curved surface. Each one of these slices is analyzed as to the weight of the slice, the normal force, the driving force, the resisting force, frictional resistance, cohesive shear strength. So all this is put together into an analysis which will give you a factor of safety. In this case, the factor of safety is only 0.97, which means you have an unstable slope. And this is exacerbated by the condition of groundwater, which gives you buoyant force, which can weaken material by separating grains and adding to the weight of the driving forces. So what do? We can reconstruct, re-engineer a slope. We can put in, let's say there's a pond up here. We can divert the water away from this existing failed slope. We can put in drains to drain the slope to lower the water table, which weakens the material. So, and we can put in a resisting or restraining wall, as you see here. So drainage and increasing resisting forces will help stabilize this slope condition. Here in this photograph, we have what's called a gabion wall. It's very simple and easy to construct. It's just a series of wire cages placed end to end and stacked one on top of each other that are filled with very heavy rock cobbles. The aim of that is to increase the resisting forces and stabilize the slope, and effectively hold the slope back. So here's another graphic showing what we can do. We can, let's see, we can put in a wall here. We can reinforce the soil with what are called geosynthetic sheets, as you see here, here, and here. That strengthens the soil mass behind the restraining wall or retaining wall. So when you consider what makes a rock slope stable or unstable, it's not necessarily controlled entirely by the strength of the rock. It may be controlled by discontinuities, bending planes, faults, joints, or fractures. When a rock slope fails, it often fails along a fracture, or along a joint, or along a fault, or along a bending plane. So you may have shallow failure, rock failure. Structural continuities control the strength of the rock mass and the ability of the rock mass to stand by itself without failing. You can have interlocking masses of soil and rock blocks, but no dominant orientation. So all those types of discontinuities, those fractures, especially if they're dipping out of a slope, can lead to slope failure. If they're dipping away from the face of the slope into the hill, it's probably a more stable situation. Some photos of rock failures in Blue Ridge Parkway, so North Carolina, Virginia, that area. So you have rock slabs sliding along fracture, fairly shallow, but the failure took place along a pre-existing discontinuity, fracture, or joint. Here you have structural rock wedge failures. So in this case, you have a fracture going this way, which leads to what we call a wedge failure, which fails along this direction. So it's like perhaps a diamond-shaped block, which, because of the orientation of these intersecting fractures, gives you a preferential failure direction along this orientation. So here you have one way to stabilize a rock slope that's full of fractures. You can put up many rock bolts. So a rock bolt is emplaced by drilling borings into the face of slope from face into the hill, and putting in steel bars, which are then cemented in. So you have a reinforcing grid of steel holding that slope back to prevent failure. Another useful, cheaper probably measure you can take if you have rock fragments or rock slabs failing from a rock face, you can confine, the failures may still occur, but the rock that comes out of the slope may be confined by a mesh that's placed over the entire slope, catching any debris.